represent each of these positions, and each row here stands in for that position and is processed by the transformer to recover all the relative positions and sort of realize which token is where and attend to them depending on their position, not just their content. So when we actually just look into an individual column inside these, and I just grabbed 3 random columns, you'll see that, for example, here we are focusing on every single channel, and we're looking at what that channel is doing as a function of position from 0 to 1023, really. Thing after to they are, you can tell, for example, that because they're a bit more jagged and they're kind of noisy, you can tell that this model was not fully trained. And the more trained this model was, the more you would expect to smooth this out. And so this is telling you that this is a little bit of an under-trained model. But in principle, actually, these curves don't even have to be smooth. This should just be totally random noise. And in fact, in the beginning of the optimization, it is complete random noise because this position embedding table is initialized completely at random. So in the beginning, you have jaggedness, and the fact that you end up with something smooth is already kind of impressive. That just falls out of the optimization, because in principle, you shouldn't even be able to get any single graph out of this that makes sense. But we actually get something that looks a little bit noisy, but for the most part looks sinusoidal-like. In the original transformer paper, the attention is all you need paper, the positional embeddings are actually initialized and fixed, if I remember correctly, to sinusoids and cosines of different frequencies. And that's the positional encoding, and it's fixed. But in GPT-2, these are just parameters, and they're trained from scratch, just like any other parameter. And that seems to work about as well. And so what they do is they kind of like recover these sinusoidal-like features during the optimization. We can also look at any of the other matrices here. So here I took the first layer of the transformer and looking at like one of its weights and just the first block of 300 by 300. And you see some structure, but like, again, like who knows what any of this is. If you're into mechanistic interpretability, you might get a real kick out of trying to figure out like what is going on, what is this structure, and what does this all mean. But we're not going to be doing that in this video. But we definitely see that there's some interesting structure, and that's kind of cool. What we're mostly interested in is we've loaded the weights of this model that was released by OpenAI. And now using the Hugging Face transformers, we can not just get all the raw weights, but we can also get the what they call pipeline and sample from it. So this is the prefix, hello, I'm a language model, comma, and then we're sampling 30 tokens, and we're getting 5 sequences, and I ran this, and this is what it produced. Hello, I'm a language model, but what I'm really doing is making a human readable document. There are other languages, but those are ... So you can read through these if you like, but basically these are 5 different completions of the same prefix from this GPT-2 124M. Now, if I go here, I took this example from here, and sadly, even though we are fixing the seed, we are getting different generations from the snippet than what they got. So presumably the code changed. But what we see though at this stage that's important is that we are getting coherent text. So we've loaded the model successfully. We can look at all its parameters, and the keys tell us where. So here's what I came up with. Basically, we see that the main container here that has all the modules is called transformer. So I'm reflecting that with an NN module dict. And this is basically a module that allows you to index into the submodules using keys. Just like a dictionary, strings. Within it, we have the weights of the token embeddings, WTE, and that's an NN embedding, and the weights of the position embeddings, which is also just an NN embedding. And if you remember, NN embedding is really just a fancy little wrapper module around just a single array of numbers, a single block of numbers, just like this. It's a single tensor. And NN embedding is a glorified wrapper around a tensor that allows you to access its elements by indexing into the rows. Now, in addition to that, we see here that we have a .h, and then this is indexed using numbers instead of indexed using strings. So there's a .h, .0, 1, 2, etc., all the way up till .h.11. And that's because there are 12 layers here in this transformer. So to reflect that, I'm creating also an h, I think that probably stands for hidden. And instead of a module dict, this is a model list. So we can index it using integers exactly as we see here, .0, .1, 2, etc. And the module list has n layer blocks, and the blocks are yet to be defined in a module in a bit. In addition to that, following the GPT-2 paper, we need an additional final layer norm that we're going to put in there. And then we have the final classifier, the language model head, which projects from 768, the number of embedding dimensions in this GPT, all the way to the vocab size, which is 50,257, and GPT-2 uses no bias for this final sort of projection. So this is the skeleton, and you can see that it reflects this. So the WTE is the token embeddings. Here it's called output embedding, but it's really the token embeddings. The PE is the positional encodings. Those two pieces of information, as we saw previously, are going to add and then go into the transformer. The .h is all the blocks in gray, and the LNF is this new layer that gets added here by the GPT-2 model. And LM head is this linear part here. So that's the skeleton of the GPT-2. We now have to implement the block. Okay, so let's now recurse to the block itself. So we want to define the block. So I'll start putting them here. So the block, I like to write out like this. These are some of the initializations, and then this is the actual forward pass of what this block computes. And notice here that there's a change from the transformer again that is mentioned in the GPT-2 paper. So here, the layer normalizations are after the application of attention or feed forward. In addition to that, note that the normalizations are inside the residual stream. You see how feed forward is applied and then this arrow goes through and through the normalization? So that means that your residual pathway has normalizations inside them. And this is not very good or desirable. You actually prefer to have a single clean residual stream all the way from supervision, all the way down to the inputs, the tokens. And this is very desirable and nice because the gradients that flow from the top, if you remember from your micrograd, addition just distributes gradients during the backward stage to both of its branches equally. So addition is a branch in the gradients. And so that means that the gradients from the top flow straight to the inputs, the tokens, through the residual pathways unchanged. But then in addition to that, the gradient also flows through the blocks, and the blocks contribute their own contribution over time and kick in and change the optimization over time. But basically, clean residual pathway is desirable from an optimization perspective. And then this is the pre-normalization version, where you see that Rx first goes through the layer normalization and then the attention, and then goes back out to go to the layer normalization number 2 and the multi-layer perceptron, sometimes also referred to as a feed-forward network or an FFN, and then that goes into the residual stream again. And the one more thing that is kind of interesting to note is that recall that attention is a communication operation. It is where all the tokens, and there's 1024 tokens lined up in a sequence, and this is where the tokens communicate. This is where they exchange information. So attention is a aggregation function. It's a pooling function. It's a weighted sum function. It is a reduce operation. Whereas MLP, this MLP here happens at every single token individually. There's no information being collected or exchanged between the tokens. So the attention is the reduce and the MLP is the map. And what you end up with is that the transformer ends up just being a repeated application of map reduce, if you want to think about it that way. So this is where they communicate, and this is where they think individually about the information that they gathered. And every one of these blocks iteratively refines the representation inside the residual stream. So this is our block, slightly modified from this picture. Okay, so let's now move on to the MLP. So the MLP block, I implemented as follows. It is relatively straightforward. We basically have two linear projections here that are sandwiched in between the Gelu nonlinearity. So nn.Gelu approximate is 10h. Now when we swing over to the PyTorch documentation, this is n.Gelu, and it has this format, and it has two versions. the original version of Gelu, which we'll step into in a bit, and the approximate version of Gelu, which we can request using 10H. So as you can see, just as a preview here, Gelu is basically like a ReLU, except there's no exactly flat tail here at exactly 0. But otherwise it looks very much like a slightly smoother ReLU. It comes from this paper here, Gaussian error linear units. And you can step through this paper, and there's some mathematical kind of like reasoning that leads to an interpretation that leads to the specific formulation. It has to do with stochastic regularizers and the expectation of a modification to adaptive dropout. So you can read through all of that if you'd like here. And there's a little bit of a history as to why there's an approximate version of Gelu, and that comes from this issue here, as far as I can tell. And in this issue, Daniel Hendricks mentions that at the time when they developed this nonlinearity, the ERF function, which you need to evaluate the exact Gelu, was very slow in TensorFlow, so they ended up basically developing this approximation. And this approximation that then ended up being picked up by BERT and by GPT-2, etc. But today, there's no real good reason to use the approximate version. You'd prefer to just use the exact version, because my expectation is that there's no big difference anymore. And this is kind of like a historical kind of quirk. But we are trying to reproduce GPT-2 exactly, and GPT-2 used the 10H approximate version, so we prefer to stick with that. Now, one other reason to actually just intuitively use Gelu instead of ReLU is previously in videos in the past, we've spoken about the dead ReLU neuron problem, where in this tail of a ReLU, if it's exactly flat at 0, any activations that fall there will get exactly 0 gradient. There's no change, there's no adaptation, there's no development of the network if any of these activations end in this flat region. But the Gelu always contributes a local gradient, and so there's always going to be a change, always going to be an adaptation, and sort of smoothing it out ends up empirically working better in practice, as demonstrated in this paper, and also as demonstrated by it being picked up by the BERT paper, GPT-2 paper, and so on. So for that reason, we adopt this nonlinearity here in the GPT-2 reproduction. Now, in more modern networks, also like Llama 3 and so on, this nonlinearity also further changes to Swiglu and other variants like that. But for GPT-2, they use this approximate Gelu. Okay, and finally, we have the attention operation. So let me paste in my attention. So I know this is a lot, so I'm gonna go through this a bit quickly, a bit slowly, but not too slowly, because we have covered this in the previous video, and I would just point you there. So this is the attention operation. Now, in the previous video, you will remember, this is not just attention, this is multi-headed attention, right? And so in the previous video, we had this multi-headed attention module, and this implementation made it obvious that these heads are not actually that complicated. There's basically, in parallel, inside every attention block, there's multiple heads, and they're all functioning in parallel, and their outputs are just being concatenated, and that becomes the output of the multi-headed attention. So the heads are just kind of like parallel streams, and their outputs get concatenated. And so it was very simple and made the head be kind of like fairly straightforward in terms of its implementation. What happens here is that instead of having two separate modules, and indeed many more modules that get concatenated, all of that is just put into a single self-attention module. And instead, I'm being very careful and doing a bunch of transpose, split tensor gymnastics to make this very efficient in PyTorch. But fundamentally and algorithmically, nothing is different from the implementation we saw before in this Git repository. So to remind you very briefly, and I don't want to go into this in too much time, but we have these tokens lined up in a sequence, and there's 1,020 of them. And then each token at this stage of the attention emits 3 vectors: the query, key, and the value. And first, what happens here is that the queries and the keys have to multiply each other to get sort of the attention amount, like how interesting they find each other. So they have to interact multiplicatively. So what we're doing here is we're calculating the QKV, we're splitting it, and then there's a bunch of gymnastics, as I mentioned here. And the way this works is that we're basically making the number of heads, NH, into a batch dimension. And so it's a batch dimension just like B, so that in these operations that follow, PyTorch treats B and NH as batches. and it applies all the operations on all of them in parallel, in both the batch and the heads. And the operations that get applied are, number one, the queries and the keys interact to give us our attention. This is the autoregressive mask that makes sure that the tokens only attend to tokens before them and never to tokens in the future. The softmax here normalizes the attention, so it sums to 1 always. And then recall from the previous video that doing the attention matrix multiplied with the values is basically a way to do a weighted sum of the values of the tokens that we found interesting at every single token. And then the final transpose, contiguous, and view is just reassembling all of that again. And this actually performs the concatenation operation. So you can step through this slowly if you'd like, but it is equivalent mathematically to our previous implementation. It's just more efficient in PyTorch. So that's why I chose this implementation instead. Now, in addition to that, I'm being careful with how I name my variables. So for example, Caten is the same as Caten. And so actually our keys should basically exactly follow the schema of the Hugging Face Transformers code. And that will make it very easy for us to now port over all the weights from exactly this sort of naming conventions, because all of our variables are named the same thing. But at this point, we have finished the GPT-2 implementation. And what that allows us to do is we don't have to basically use this file from Hugging Face, which is fairly long. This is 2,000 lines of code. Instead, we just have less than 100 lines of code, and this is the complete GPT-2 implementation. So at this stage, we should just be able to take over all the weights, set them, and then do generation. So let's see what that looks like. Okay, so here I've also changed the GPT config so that the numbers here, the hyperparameters, agree with the GPT-2 124M model. So the maximum sequence length, which I call block size here, is 124. The number of tokens is 5257, which if you watch my tokenizer video know that this is 50,000 merges, BPE merges, 256 byte tokens, the leaves of the BPE tree, and one special end of text token that delimits different documents and can start generation as well. And there are 12 layers, there are 12 heads in the attention, and the dimension of the transformers was 768. So here's how we can now load the parameters from Hugging Face to our code here and initialize the GPT class with those parameters. So let me just copy paste a bunch of code here. And I'm not going to go through this code too slowly, because honestly, it's not that interesting. It's not that exciting. We're just loading the weights. So it's kind of dry. But as I mentioned, there are 4 models in this mini series of GPT-2. This is some of the Jupyter code that we had here on the right. I'm just porting it over. These are the hyperparameters of the GPT-2 models. We're creating the config object and creating our own model. And then what's happening here is we're creating the state dict, both for our model and for the Hugging Face model. And then what we're doing here is we're going over the Hugging Face model keys, and we're copying over those tensors. And in the process, we are kind of ignoring a few of the buffers. They're not parameters, they're buffers. So for example, attention.bias, that's just used for the autoregressive mask. And so we are ignoring some of those masks, and that's it. And then one additional kind of annoyance is that this comes from the TensorFlow repo, and I'm not sure how, this is a little bit annoying, but some of the weights are transposed from what PyTorch would want. And so manually, I hard-coded the weights that should be transposed, and then we transpose them if that is so. And then we return this model. So the from pre-trained is a constructor or a class method in Python that returns the GPT object if we just give it the model type, which in our case is GPT-2, the smallest model that we're interested in. So this is the code, and this is how you would use it. And we can pop open the terminal here in VS Code, and we can Python parameters of the GPT-2 models. We're creating the config object and creating our own model. And then what's happening here is we're creating the state dict, both for our model and for the Hugging Face model. Okay, now before we can actually generate from this model, we have to be able to forward it. We didn't actually write that code yet. So here's the forward function. So the input to the forward is going to be our indices, our tokens, buffers. They're not parameters, they're buffers. So for example, attention.bias, that's just used for the autoregressive mask. And so we are ignoring some of those masks, and that's it. And then one additional kind of annoyance is that this comes from the TensorFlow repo, and I'm not sure how, this is a little bit annoying, but some of the weights are transposed from what PyTorch would want. And so manually I hard-coded the weights that should be transposed, and then we transpose them if that is so. And then we return this model. So the from pre-trained is a constructor or a class method in Python that returns the GPT object if we just give it the model type, which in our case is GPT-2, the smallest model that we're interested in. So this is the code, and this is how you would use it. And we can pop open the terminal here in VS Code, and we can Python train GPT2.py, and fingers crossed. Okay, so we didn't crash.